Cool, thank you. The last talk is from Liquan, and he's going to talk about the change data capture in distributed databases. So one very common use case of Kafka is actually called event sourcing, where you want to actually derive your updates from the real-time LTP systems and into a different OLAP query handling system, so that you can have real-time query serving from your distributed systems. And Liquan have done some deep dive into two of the modern distributed databases, CockroachDB and TiDB, and he's going to share with you his studies about how to use Kafka to do CDC and how that actually is applied with common distributed database system scenarios. Thank you, Liquan.
Okay, thank you for the introduction. So which is my, okay, cool. Okay, so yeah, this is going to be my talk. And so before I talk to the main content, I'll quickly go through the Pinterest does. So Pinterest is a visual discovery engine, and it has a lot of monthly active users, and it has a lot of pins created by people. So it has a lot of recommendation made to the users per day. So it's a great platform for ads. So I'm working on the ads infra team, at Pinterest, and our team is building the ads platform for Pinterest. And if you are a user of Pinterest, and each time you open the app, you will see organic content plus some ads, and they are nicely blended so that you won't even notice that there are ads there. And this is because of our team's responsibility, and we did a very good job building the platform so that you won't be bothered by irrelevant ads. If you are curious about how this is built, and there's a link there, and it points to Boyan and my talk at last year's Kafka Summit, and how do we use Kafka streams to actually building this kind of stuff, and which I'm not going to talk about. And another one is kind of like a quick advertisement. And in this year's Kafka Summit, and Boyan and I, unfortunately, Boyan is no longer working at Pinterest, and it's just talk about this. So we're going to give a deep dive on actually a static membership. And this kind of a new rebalance strategy that is very good for the cloud, and it can actually improve the availability of Kafka Stream applications. I encourage you to attend talk if you are interested. So this is the main talk. So I believe that you have enjoyed your July 4th vacation, and I believe before that, you probably make some hotel reservations through some websites, right? And this is an example I want to show you how you can really build a kind of a scalable applications using the database, Kafka, and change data capture. So I think the use case is pretty simple. You want to book a room, right, for duration of stay. And then actually what you need is that you want to find the available room, and you want to book the rooms, right? But behind the scene, as a business owner of the hotel booking application, they actually want to do a little bit more things, right? They want to do some flash sale so that they can earn money, and they also want to give you some book history, and they will analyze the book history to give you some recommendations of the hotel so that they can earn more money. More important, sometimes they want to do dynamic pricing, because I believe that at July 4th, people want to go to some places, and if the place become hot, they will track the demand and the supply and adjust the price dynamically so that they can kind of get a better return on the hotel rooms. So if you build those kind of systems, you need to be high uptime. You need to have low latency, because then you want your application to be able to scale to increasing number of users, right? It's kind of like a typical architecture these days. You have web app, you use a database for serving this web app, and then some things like the dynamic pricing involves you analyze the booking of kind of the hotels and do real-time analytics on those to make real-time decisions. And this actually you need to get your changes on your database, because once you make a hotel room reservation, you actually need to append the entry in your order table, and this can also emit a change of this append. And then you can actually analyze that change and group by by different hotels so that you can dynamically adjust the price. So this is kind of a very typical cases of a scalable applications. And one thing I want to say is that typically the other part, like the Kafka part and all the analytical part, is actually very scalable already these days. But a hard piece of this is like your transaction database is very hard to scale. And even if you don't scale, many times you have to do it manually. So this causes a lot of trouble. That's why recently this year you have those distributed databases. They try to handle a lot of things you have to do manually to be automatically, so that you can really treat it a sharded database to be actually kind of like a single instance database without worrying about the sharding and the data distribution and things like that. So these are TiDB. TiDB is a distributed database, and it has a KV layer and a kind of serving layer. And I will talk about details. This is just how it works, and it has been adopted by many companies actually. So because this is a Chinese company, so it's a lot of companies are currently in China, because I think they kind of like treated this as a way of replacing MySQL sharding, as well as treat it as a scalable NoSQL solution. If you can write SQL to do the same thing, you will write SQL, you will not write code, right? That's kind of the motivation. And the similar story with the CockroachDB, it kind of following the very similar architecture. Base have a transactional key value layer as well as SQL layer. A little bit different is that TiDB kind of like has a centralized service called the placement driver to manage all the metadata. This one is, you can think it as a zookeeper to Kafka. So this one kind of CockroachDB kind of manage those metadata on its own. Okay. So it also has a lot of adoption. Sorry about that. This is all I can find in the website. So I believe there will be more, but so I don't want to give an impression that this is not a fair comparison. But in general, it's a lot of companies starting to adopting them to building applications. So I think if you want to build a database, especially you build a distributed database, I think there are kind of two major problems to solve. One is that because it's a distributed database, you want to have a distribution strategy, right? Typically, you have a hash partition and you also have a range partition. And then for hash partition, it is easy because you can use a hash function to find the key, and from key you know which node you store this key. But for range partition, actually you don't know that. Then you need a kind of a third party that kind of manages the mapping between range and machines. And then if you're building a distributed database, and one importance is that this has to be very resilient, because kind of things are kind of, if you are running things at scale, things get failed basically every time. So you kind of need to do some replication, and this replication is done through Raft consensus protocol. In general, both in CockroachDB and TiDB, they try to partition the data by ranges, and their kind of unit of their partition is called a region or range, and this region or range are replicated into multiple copies using Raft. Yeah, and each region has its own Raft, has its own Raft group, and the application kind of composed of a multi-Raft is kind of a group of Raft groups. Okay, so if you are familiar with Raft, so each region, they will maintain a kind of a log, and this log will be applied on different regions so that you can get a consistent view of your state by applying those logs. If you do this kind of architecture, it's pretty easy to scale things, because once you add a new machine, you can just create a new copy of data and replicating the data to the new node, and then deleting the data from the old node. So, and this can be done in a transparent way to the applications. So another part of a database is that you want to support transaction. And I think it calls ACID property, but what really matters is that you want to do things in an atomic way. And then you want to do things that basically, there are two things that matter. One is atomicity. You want to make changes to multiple data, and these changes are visible to other transactions at the same time. The second one is that once you make changes, you don't want to generate some anomalies. For example, if you book a hotel room, right? Basically, you don't want to a hotel room to be booked by 2 people. So you need to schedule transactions so that these anomalies will not happen. One kind of analogy to the transaction is actually the multi-threaded programming. You have multiple threads accessing a shared piece of data, and need to make sure that when you access data, you basically maintain some kind of consistent state of your shared data. That is complicated, but you can actually schedule transaction in a purely sequential fashion so that there won't be any anomalies, and this is called serializable. But in practice, this is very expensive, and and the overall throughput will not be high. And then by analyzing the use cases, and you can really relax this and to allow more kind of different ways of scheduling your concurrent transactions so that you get different isolation levels and to trade off between the performance as well as kind of isolation between different transactions. Okay, if you want to do transaction and maintain a certain level of isolation, there are a couple ways to do that. One is locking. Locking is like when you access data, you need to acquire a lock and get the result of this. This is the first part. But if you do that, which means that a lot of transactions a lot of schedules are not allowed. And the second one is you do optimistic concurrency control, which means that you create a copy of all the data you want to modify and make changes in the copy. And then at the time of commit a transaction, you actually write the data to the shared space. And during the time you write, you check whether there are modifications by the other parties. And then if there are conflicts, you abort. But if there are no conflicts, you kind of commit and make your changes available to other party. So multi-version concurrency control is kind of a trade-off between these two. On one hand, when you write the data, you don't just acquire log. You basically create a new copy of the data. And when you read it, you read by a timestamp or by a version, and you get the latest committed version, so that the read transactions will not be blocked by ongoing writes, and in reality, a lot of majority of the transaction will be read transactions, so that it can have high throughput. So now I'll talk a little bit about the kind of how the multi-version concurrency control work. Basically, instead of just storing the data, you're also storing a version with the data. And when you write to a certain piece of data, you create a new version of that data. And I have to talk about, because of this, any read will not be blocked by any writes. And this is actually inspired by the compare and swipe, which is CES in the multi-threaded programming. Basically, you make changes on your private memory, and then you write back and you check whether there are other parties making changes to this data set. And how the transaction work. As I said, one goal of transaction is that you want to make modifications to multiple data to be visible to the other transactions at the same time. So there has to be a stage you want to make sure that a change is actually pending. It's not yet visible to other transactions. Then in the MVCC, when you write data, you kind of like leave a mark there. It's called log in TiDB, and it's called intent in CockroachDB. This mark, the existence of this mark in the storage indicates that for this version of data, it's not yet, it is modified by an ongoing transaction. So it's not yet visible to you when you try to read it. Yes, so a general way of doing kind of like basically a practical snapshot isolation level is called snapshot isolation. What it means that you can really like when you read your database, you can get a consistent copy by a starting timestamp. By this I mean, assuming we have globally all the timestamp, we'll talk about how do we achieve this in a distributed system environment. Assuming you have this, once a transaction tries to read the data, they will first get a timestamp, and you will read all the keys with this timestamp. Once you read it, they will give you the committed version before this timestamp. And this is true for all the keys this transaction tries to touch. That's why it's called a consistent snapshot, because it's a consistent view at this timestamp. And once you try to commit, it also gets another timestamp. It's called commit timestamp. And this timestamp will be true for all the transactions, for all the writes this transaction has made. Suppose a transaction cannot multiply 3 keys. All the 3 keys will have a commit timestamp, have the same commit timestamp. That's why I call it snapshot isolation. And the way to work that is first get a consistent copy of data through a timestamp. And once it's a commit, it will also get a commit timestamp. And this is consistent across all the keys this transaction touches. But before transaction can commit, it needs to check whether the data this transaction modified has been touched or changed by other transactions, because we don't have a log. So when one transaction is in progress, the other transaction can modify the data as well. So we need a mechanism to kind of reject other transactions if there are conflicts. And there are kind of different ways of conflicts. You can have 2 transactions write the same piece of data, and they can be concurrent. You can also have one transaction write the data, and then at the same time another concurrent transaction read this copy of data. You can also have your copy of data be overwritten by another transaction. So typically, people will use called a serializability graph to represent these transactions. And this is important in making sure that only certain transactions are allowed to execute at the same time, or allowed to commit when they run in concurrently. So suppose we have 2 transactions. One is that at start time, T1 starts at this start timestamp, and then T2 at a later time. And then T1 may make some changes, and T2 will maybe commit earlier. And when you try to commit, you will try to check whether the keys or the data the T2 touches has been modified by T1. If there's no, it will be commit. And then T1 will do the same thing when it tries to commit. So the condition that T2 can commit is that when it checks the conflict, you check that whether there is any ongoing transaction that modifies the key modified by that is modified by T1. Okay, let me say this guy. So suppose there's a data point is modified by T2, and then once you try to commit, you check whether this data point be modified by T1. There are 2 cases. One is that this data point is modified by T1, but T1 is not committed. This means that there will be a mark there indicating that this ongoing transaction is modifying this data point. Or the other transaction committed, and then you will see that there will be a version larger than the starting timestamp that is committed, so you will abort, basically. And all this check is only valid only if you have a notion of global ordering of time. Same thing here. So this is basically how the snapshot isolation work. Or how the multi-version concurrency control work. This is one part. The other part is that how do we kind of like making sure that multiple modification of multiple keys are visible to the other transaction at the same time. Basically, you don't want this to happen. You want all these three changes, they are either visible to the other ones or none of them are visible to the other ones. That's why you need a two-phase commit, because in this case, because we are doing multi-version concurrency control, which means that these keys can be modified by the other transactions at the time of commit. So before it can commit, it needs to make sure that there are no conflicts to all these participating keys. And this cannot be done. It cannot be done like in one step. You have to do it in twice. Once you pass this check, which means that there's no any conflicts on all the participating keys, then you can commit. It's the same as a Kafka case, and you have to commit. The way you do that is that you choose one key as your primary key, and you make this key visible to the other transactions. And once this is done, all the other keys have to commit. And the way it works is that for the other keys other than primary key, you have pointer to your primary key and your start timestamp of your transaction, so that even if the other keys cannot commit due to some failure cases, when the other transaction checks this key, you can check the state of the primary key and determine whether this transaction is committed or not. And then this makes sure that anything that committed, even this change are happening in multiple keys, or these multiple keys can be in multiple machines, they can be done in atomic fashion. So this has to be designed in a way that the transaction or anything can fail at any time. So to sum up, if you want to build a distributed databases, there's one way that you partition your data into small regions, and you replicate each region through Raft. And you can use multi-version concurrency control to achieve snapshot isolation level. And you use the two-phase commit to ensure that changes to multiple keys are kind of like visible to other transactions at the same time. And one important thing is that if you want to do this, you need a kind of global ordering of the transactions. And here I use the notion of timestamp. And we all know that in distributed systems, there's no different machines have different timestamp. And there has to be some solution to generate this globally ordered timestamp. TiDB uses a version of kind of like a single node solution. In the TiDB, there's a designated service called a playback driver. That one is responsible for generating the unique timestamp. And in CockroachDB, there's a notion called hybrid logical clock. And they use both the physical time and the logical time to create ordering of events with some kind of granularity, kind of uncertainty. So to make sure that with this certain uncertainty bound, you can order things. But the HLC has a kind of like a shortcoming in that it relies on the NTP protocol, which has high uncertainty. And Google kind of invent called a true time API to reduce this uncertainty, so that this can be to improve the performance, because you cannot commit the transactions if you cannot differentiate the order of two things. One transaction has to be retried, right? So this means that this limits the throughput of your transaction, your database. So the less uncertainty you have, the more transaction you can execute it per second, which is to improve the throughput of your databases. Okay, that's for the distributed databases. And sorry for the kind of the long introduction. Now we're going to talk about the CDC here. Why I need this kind of like a long story? Because I talk about, so the distributed databases support distributed transaction, and they use rich partitions, right? Which means that a transaction can actually span multiple nodes and span multiple regions, right? And if you want your change data capture to be able to support like the MySQL Binlog to be able to support backup and recovery, you need to actually order these transactions in a transaction ID order. You need to globally order them. But the reality is that all this, because these transactions are kind of like executed in multiple nodes, the data actually live in multiple nodes. You actually you actually need to kind of merge multiple node by a. So the data so basically you need to generate a global order of events by merging multiple order of events with very low latency, and this has to be highly available. So it'll become evident later that this is very challenging. So there are two ways to do this. The first one I'll talk about the easy stuff is actually you do the row level change without. The second one is challenging is that you need a transaction order change. So first of all, because for both RocksDB and both CockroachDB and TiDB, they use Raft to do replication, and this means that for each region, they actually have a Raft log, and this Raft log records all the changes to the data stored in this region. Actually, if you kind of expose this data to Kafka, you actually get a binlog because your Raft log is actually the red hat log for a small region of your data. So, but this is easy, right? Because even if like a table can span multiple regions, but one row will be only one region, it only become one Raft group. So the Raft log will be the content of the Raft log will be the same as changes to the row in a single row. This is how CockroachDB does, and basically each range will expose the leader will expose the red hat log, the Raft log to Kafka. So then you will get ordered events for a certain row, right? This is pretty obvious. So this can offer at least once guarantee, and you can get all the changes to a certain row in order, and they are guaranteed to be linearizable because once you see a row with a higher timestamp, they won't go back because we are using Raft to guarantee this. But this is useful because if you only care about changing to a single row, and you basically, this can solve your problem. And this can also be driven by, this can also solve the problem of our hotel booking case because only care about the single row change. And then you can basically do all this stream processing by that. But it will not be suitable for other cases, like if you want to do a backup of database, you have to order the changes by the transaction ID because you start from the clean state. You will have to apply all the changes, all the transaction changes by the transaction ID order to guarantee a consistent state as a primary database. So that definitely has is more difficult because you kind of need to create a global ordering and you don't know like when will be the next event to happen. So, and also another challenge is that you need to have relatively low delay to downstream. And how this can be done? And this is basically how the TiDB approach, and it has a component called Binlog. And it collects the logical changes made to a cluster. And it can synchronize between different clusters. The way it works is that basically the cluster gathering the binlog also need to be highly scalable, because the goal of distributed database is that by adding more machines, it can support more transactions per second. The more transactions you have, the more changes to your database will have, right? So your service gathering those changes needs to be able to scale linearly with the number of transactions. This means that you need really a scalable solution. So that's why you need a cluster solution. But another challenge is that this cluster solution, they can generate partial orders, but they cannot generate global orders. In order to generate global order, you actually somewhere need a single reducer or single aggregator to aggregate those logs and create a ordered events, globally ordered events. There's a drainer part. Here, although we have multiple instances of drainers, each drainer needs to create one globally ordered stream, and different drainers kind of supporting different things, okay? This is how a binlog looks like. You can, when you make some changes to your database, it converts to a sequence of inserts and deletes. And this one will be packed to one message and will be sent to downstream. Okay, how TiDB writes binlog? As I mentioned before, the TiDB actually does two-phase commit, and the write to binlog also happens during the two-phase commit. During the pre-write to TiKV, and there will be a synchronous write to the binlog, and during the commit phase, there will also be an async write commit to the pump, and the reason to do this is because the prepare phase, there's more work. As you have to write the data to your kind of key value store. And on the commit phase, you only need to basically change this one row and make it visible. So if you combine this two binlog to a single binlog at commit phase, your transactions through your database throughput will be limited because you write a lot of data to downstream during commit phase, so you cannot become the bottleneck. So to avoid those bottleneck and achieve high throughput, you actually try to write the binlog during the pre-write phase, and the pump basically will be taking those log files, and you can think about the log file be append-only file. It will kind of append a new entry to a binlog as a message contains a sequence of updates, deletes, and inserts. And the key value database will store the position and start timestamp of the transaction, and it's basically for the lookup. One importance of the pump is that it will basically create partial order of the binlogs. And this also makes sure that it can have max commit timestamp indicating the maximum timestamp of a committed transaction. Why this is important? As I mentioned, for certain transaction, there will be two binlog messages. It can be the case that you have a prepared binlog receive the pump, but not the commit log. So you need a mechanism to ensure only both binlog are received by the pump. You can basically export this to the downstream drainer to generate the globally ordered event stream. The responsible drainer is to fetch the binlog for all the pumps that are registered and create a global order. So why this is interesting? Because there can be the case that you have merged the log of the drainer of 1, 2, 3, but certainly pump 1 become unavailable. then how do you handle this case, right? That is one case. Because in this case, if pump is not able to recover, you cannot really make progress. Because if you don't consider that case, you merge number 5 here, you kind of basically lose some data. So you need to make sure that all these pumps and drainers are kind of highly available so that any failures of this pump will not block the drainer. Also, another thing is that even the other case is that you have a new pump join the system and start like accepting the kind of the Binlog messages. Drainer has to first be notified by knowing that the newly joined pump is there so that it can, otherwise, the Binlogs gathered by the newly joined pump will not be kind of like guided by the drainer because it can actually get the next available Binlog from the other pumps without knowing that the new pump has actually have a lower timestamp. Okay. Also, in order to make progress, pump needs to send fake log to itself to ensure the progress. Why this is the case? Because a pump can become the case that in not receiving any Binlogs in a certain period of time. And then in this case, drainer cannot make progress because it doesn't know any progress in this pump. So it needs to send some heartbeat or fake log to itself to ensure that, okay, I have a fake log here to ensure that to let the drainer know that there are no actually true Binlog, and then you can get the next available Binlog from the other pumps, right? Okay.
Are these numbers strictly incremental?
Yes.
So I can detect if numbers.
They are not strictly incremental. As I mentioned, for TiDB or CockroachDB, they are all using a globally ordered timestamp. So this means that you don't know what the next key is, right? So that's the challenge here. You have to this mechanism to ensure that you are not missing any data. So I believe that because you are using this ordered log to be to do database recovery, so you cannot really kind of correct the order, right? If you send the out of order, there will be forever there, not correct it. I would say that this is kind of the hardest stream processing problem, whereas that the progress has you only can make progress by making sure that the next available event is there. That you cannot really correct the result. So there are a couple of failure cases. Is that the drainer cases can fail, which means that you have to do some manual intervention, and also the pump interface can fail. In that case, you have to manually recover. So I think if you compare this row level change capture and with the transaction order capture, definitely the row level is easier to implement, and also it's scalable and have a lower latency. But the problem is that this cannot be used to do backup and restore. If you want to do transaction order change capture, the challenge is that the system you design is very hard to be highly available, and you can very easily run into the case that a certain piece of the system not working causes the whole system to be blocked. So there has to be some kind of like a better way to do this. I know this is a hard problem, and there are the TiDB or the community is also thinking about improve on this thing. So how many? Yeah. So how this can work is that I think the idea is pretty straightforward. It's like they will expose the Raft log starting the TiDB instead of building a new system that gathering the logs. Similar as what we do for stream processing, we kind of has a concept of watermark. What the watermark means is that before the watermark is treated as timestamp, they call it a checkpoint timestamp. All that means that anything happened before this checkpoint time means that all the changes all the transactions happened before the checkpoint time are already applied and reflected in the Raft log and the database state. If you know that, and if you know your previous checkpoint timestamp, and the transaction happened between these two timestamps are guaranteed to, you basically have all the events, you have all the messages in this time, this time range. This is like a mini batch, right? You wait a certain period of time, you'll make sure that things happen in this meantime. You gather all the messages. If you expose those messages to the downstream, you can reconstruct the transaction happened in this interval, globally order them, right? Okay, and then you make progresses. I think the trade-off is that in this case, you cannot really like guarantee very low latency, but the trade-off is that you won't suffer data loss like the previous solution have for the PAM solution because that one is not replicated. Okay. But another thing is that can we actually avoid doing this change data capture at all, right? And there's also some interesting idea. It's like instead of like building the Kafka log to do that, you actually can use Raft replication to create another Raft learner state that can purely used for the real-time analytics. And this basically eliminates the need for the CDC for some cases, but not all the cases. So I think the takeaway is like that. So if you have a distributed database, you can simplify scaling of your applications. And also the CDC is very important in making real-time decisions for the success of business. But there are a couple of challenges to the CDCs in distributed systems in that you need to gather changes across instances and also need to guarantee that the changes sent to downstream in the logical order of transactions. And and you also need to make sure the system are highly available and have a low latency. So you can roughly avoid them by using some other mechanism. And thanks for these people. And they probably a lot of feedback, especially Boyang. And he criticized me about the quality of the slides yesterday. So I make a lot of improvements today. So thank you. Hope you enjoy.
Any questions? Okay, one quick question for Liquan, since no one asking question here. So for most of today's source Kafka connector, they are actually following the first approach that you mentioned, which is like a role-based data capture stream. What kinds of improvements you think that, for example, for a framework like Kafka Connect needs in order to do this transaction level data capture, that we can implement those approach in Kafka Connect, in source Kafka Connect, more specifically?
Okay, so you want to generate basically transactional order of events from your source connector, right? Yeah. So I think there are not much options here. You have to have a place to kind of aggregate your changes and make it to one logical one stream, right? So I think the challenge there is that you want your source connector to be highly available, which means that when you write, so basically, let's do this. So, so your system, your source connector has to maintain a state of the available sources, and then you also need to make a state you send to downstream. So, I mean, so this, yeah, you basically have to do this. I think the challenge here is that how do you making sure this state is highly available in terms of failures? Maybe okay. Maybe I didn't answer the correct answer.
I think there are some ideas about implementing this in Kafka Connect. Actually, for example, I talked to someone from Google. Actually, Spanner is also considering using Kafka for CDCs, and they are actually exactly considering using transaction level CDC instead of row level CDC because they have the exact same consistency concerns for their downstream applications. You know, so I would highly recommend you to talk to some of them for those ideas. Okay, thank you, thank you, Liquan. And so we are wrapping up today. The next event will be actually co-hosted with Bloomberg in San Francisco next month. So hope to see you there in the city next time. Thank you.